Good morning, everyone. And it's morning for me. I don't know about for you. We are diving into Unit 5, and we're starting with Topic 5.1. And Topic 5.1 is reaction rates, and a fancy name for studying rates of reactions or reaction rates is chemical kinetics. Okay? And so the study of a rate of change of concentration of substances involved in a chemical reaction. Are the reactants decreasing and the products increasing? If that's the case, that would suggest that a forward reaction is happening, right? That like reactant A is turning into product B. So if we have a decrease in concentration over here and an increase in concentration there, that means that whatever we had as A is turning into B. But how does this happen? How does our whatever our A thing is turn into whatever our B thing is? And that's what collision theory is. So let's look down here. So here's an example of what I mean. If we have carbon monoxide, okay, so carbon monoxide, and we have that react with oxygen, O2. One potential reaction for this is CO2, and then we'll have an oxygen that's left over. So it's like, how do these reactants turn into these products? Let's see if I can find a darker pen. Might be helpful. Okay. Now, in order for reactants to turn into products, there's three things that you need to know. The first one is that reactants have to collide, that if they do not collide, then a reaction doesn't occur. So collision theory, three parts. First off, reactants must collide. Okay, but it's not enough just to collide. They have to run into each other, but they have to run into each other with enough energy and proper orientation, and that's 2 and 3. So reactants must collide with enough energy and proper orientation. You know, here's what I mean. Let me grab some markers. Now, let's say that we want to have a reaction occur between these two reactants. So as they're like moving around, they have to actually collide with each other. But a collision alone is not enough. They have to collide with enough energy. If this reactant doesn't run into that reactant with enough energy, then we can't break old bonds. So we have to collide with enough energy and proper orientation. So as this is moving around the world, if it runs into it like this, that's not proper orientation. So even if it was enough energy, a reaction wouldn't occur. Maybe this is the proper orientation right here. So if it runs into it, then it can break old bonds and new ones can be formed. And then we get something new, we get these products. And that's what we see down here. This is a visual representation of having proper orientation in order for a chemical reaction to happen. So here was our carbon monoxide and here's our O2. And if they collide with this orientation, no reaction. But if we flip that carbon monoxide around, and we run into, the two molecules run into each other with this orientation, that's what allows this oxygen to chemically bond to that carbon. That there's enough energy to break this bond, and there's proper orientation to form that bond, and so then we end up with these products. So again, collision theory, reactants must collide. They have to collide with enough energy and proper orientation. Now, based on that collision theory, there are 5 factors that affect rates of reactions, and you need to relate it back to that collision theory. if we can have more collisions, then reactions are more likely to happen. If those collisions can have greater energy, then they are more likely to happen. And if we can promote proper orientation, then also reactant rates increase. It's more likely that a collision will occur with enough energy and proper orientation. And so let's see if we can remember. All these is back from like Gen Chem and Honors Chem. The first thing that we could do to make a reaction go faster or lower is changing the temperature. And maybe we could focus on just like increasing the reaction rate for this first one. And then you know that if you do the opposite, it would decrease it. So one way that we could increase a rate of reaction is by increasing the temperature. If we increase the temperature, all of a sudden these particles are moving faster. So two things, we get more collisions, they collide into each other more often, and those collisions have more energy. The other thing that we can do is that we can increase concentration. Let's put more stuff into the same amount of space. So if we think about bumper cars right now, I love this analogy, I think it works really well. So like let's get a little bumper car arena. And I've got my bumper cars in there. So if we increase the temperature, that would mean that the bumper cars move faster. So if they're moving faster, then they're more likely to run into each other, and the energy of those collisions are higher. If we increase the concentration, that means we're going to put more bumper cars in there. So as soon as we put more bumper cars, more collisions happen. So that'd be an increase in concentration, more stuff in the same given space. Another way that we can do this is that we can decrease surface area. Okay. Decrease surface area. That would increase the rate of reactions. Here's what I mean by that. Let's say we got like a clump of bumper cars over here, okay? And so it's almost like it's a solid because they're kind of stuck together. They're stuck in that corner. These guys can run into the ones on the outside, but they can't run into any of the particles that are kind of stuck in the middle of these clumps. And so because of that, that would be a bigger surface area. Sorry, a smaller, my alarm's going off. So we limit the surface area in which the particles can react. Meaning like this can run into area out here, but it can't get to anything in there. And so only by separating these out can we now have more area in which we can react. Because not only can we run into the ones on the outside right here, but even all of this area on the inside of these particles and all of that particle are not available to react. Okay. So then, our last one, so we have increase in temperature, increase in concentration. We want to, we're going to increase overall surface area, and I'll explain that more in class, give you another visual example of that one. And then our last way of affecting a reaction to make it go quicker is by adding a catalyst. Different catalysts work in different ways, but a really common way that catalysts work is they actually hold reactant particles in proper orientation, which leads to a higher likelihood of a successful collision between them. So, catalyst. Okay. like we said, kinetics is how we are measuring or the study of rates of chemical reactions. So that's like the speed at which reactants are disappearing and the speed in which products are appearing. So first thing I want you to remember is like that reactants turn into products. And when we did our BCCA table, we saw this, that when it came to reactants, so we're talking about reactants right now, we put a negative with this because they're going to be disappearing. And it's the change in, remember a little triangle, this means change in, it's like final minus initial, but it's the change in the concentration of a reactant, and I just chose one of the reactants, it doesn't matter which one, but it's the change in that concentration of that reactant over a change in time. Okay, and like I said, we need to apply this negative sign because it indicates that we're decreasing that concentration, like that concentration is decreasing over time, where products are going to have a positive, right? So like if I want to talk about the rate of appearance of a product, we would be increasing in our change in concentration. Now, again, I'm just picking one of them over our change in time. Okay. Now, here in a moment, I'm going to show you how the coefficients play into this, but right now we have an equation that doesn't have any coefficients, or all of the coefficients are the same, right? There's technically ones in front of all of those. And so what's cool about this is when these coefficients are all the same, then the rates of disappearance equals the rates of appearance. So I could say this like, and actually let's write it two ways. We're going to say negative, or really we could just do the rate of disappearance of A is going to equal the rate of disappearance of B. And again, this is because their coefficients are the same. And that's going to equal the rate of appearance for D and the rate of appearance for E. And rate is what we just wrote down here. It's the change in concentration over the change in time. So I could replace this. I could say negative change in concentration of A over a change in time will equal negative concentration, negative concentration of B over time, change in time. That equals a positive change in concentration, forgot the triangle on that one, change in concentration of D over a change in time, and positive change in concentration of E over time. And I really want to point this out because often in AP Chemistry, if you think through it in this way, you don't have to worry so much about how this is looking here. That we just need to recognize this comparisons of the rates, but know what rate is. Know that rate is a change in the concentration of an item over time, and that it will be negative when we are talking about reactants, and it will be positive when we're talking about products. Okay. Now, what do we do, though, if they don't have the same coefficients? Because here we have a coefficient of 1, a coefficient of 1, and then a coefficient of 2. So we know that when they're the same, that they equal each other. So like I could say that the rate of disappearance of N2 is equal to the rate of disappearance of O2. Like the speed at which this one is disappearing and turning into products is equal to the speed at which that one is disappearing and turning into products. But what do I do with this 2? And here's the interesting thing, is instead of saying that the rate of appearance is like 2 times the rate of appearance, it's actually 1/2 the rate of appearance of NO. That whatever the coefficient is here, that would go in the denominator there. And okay, wait, hold on. One of these results in 2 of those. So isn't this rate double? Here's what's happening. Let's ignore this rate of N2 for just a moment. Now, we are under this idea that this rate of NO should be twice the rate of O2, and I completely agree with you. But let's solve for this, because right now this is not, we're solving for 1/2 of this rate. And so if I divide both sides by 1/2, or that would be the same as multiplying this by 2, right? Another way of saying this would be 2 times the rate of O2 is equal to the rate of NO. So if you take the rate of O2 and you double it, then you get the rate of NO, and that is the case. This rate is twice as much as the rate of O2, and we see that based on the stoichiometric coefficients here. But in order to take this coefficient and place it with its own reactant or product item, we put it in a fraction so that if we ever solve for it, it would apply to the other items. Okay? Now, we can add our little fancy change in here. Like if you ever need to, or you see this on the test, just don't feel overwhelmed by this. Instead of saying rate of N2, the rate of N2 is the same as negative change in concentration of N2 over the change in time. How much is this disappearing over time? And then again, rate of O2, it's negative because it's a reactant. Change in concentration of O2 over a change in time. And then this 1/2 we pull out in front. So 1/2, and then we know what the rate is. The rate of NO, nitrogen monoxide, would be a positive, and it would be a positive change in concentration of nitrogen monoxide over a change in time. Okay? So back to this idea. And I have a new reaction for you. So we have a coefficient of 2, and then of 1. And then look at the graph here. And what if these were not labeled? NO2, O2, and NO. Could you tell me which line represents which species? First thing I want you to notice, reactants will start off high and then decrease over time. So since the fact that this one started up here and it's decreasing over time, that has to be my reactant. Since these ones are starting lower and they are increasing, then these ones have to be my products. This one increased more slowly. This one had a higher increase and a quicker change in concentration over time. And so then this one had to have the smaller coefficient in front of it, and that one had to have the bigger coefficient in front of it. If we take 2 nitrogen dioxides, they're going to produce 2 nitrogen monoxides and only 1 O2. So we're going to have less O2 being made and more nitrogen monoxide. And so that's how I could distinguish between those, that these are my products. And then we have a greater change in concentration over time. So that would be my higher coefficient, and then our lower coefficient. There was less of it that was made over time. Okay, great. Well, if rate is a change in concentration over a change in time, then what units would go with rate? First off, change in just means final minus initial. So I'm just going to go with, I'm going to actually do an easier one. Like, remember at the beginning where I said A turns into B? So if I was talking about the rate of disappearance for A, then that would mean that I have a negative, I'm not worried about that as far as units go, a change in concentration of A over a change in time. And this change in this triangle means final minus initial. So that would be concentration of A final minus concentration of A initial. Okay, concentration of A initial. Same with the time. It'd be time final minus time initial. When you add and subtract things, their unit doesn't change. Okay, so like if it was a 5 molarity minus a 2 molarity, we'd end with 3 molarity. So if you add or subtract, the units need to be the same and the unit doesn't change. When we multiply and divide, units also multiply and divide. So back to this example down here. What if I want you to solve for, including the units, the rate of disappearance for AB, okay? So under this same idea, instead of writing A, essentially we're writing AB, and we know it would be negative, and then outside of this negative, it would be the concentration of AB final minus the concentration of AB initial divided by time final minus time initial. And all that information is given to us over here. So here's our initial and here's our final. So the final concentration was 5 and the initial concentration was 15. So final concentration 5 molarity minus the initial 15 molarity. Okay, divided by time final, which was 60 seconds, minus time initial, which was 0 seconds. All right. Oh, and then don't forget we got the negative sign on the outside. So 5 minus that 15, and then so we're taking our negative 10 and we are dividing it by 60. Okay. And then there's a negative here, but there's a negative on the outside of this, so that would cancel. So that would mean the rate of disappearance for AB is equal to let's do sig figs, 3 sig figs, 4 sig figs. Let's go with 3 sig figs, 0.167. But what's my units? Concentration divided by time. Molarity per second. Or molarity second to the minus 1. Okay. We have this example problems here. And actually, I think I want to do one of these with you, and I think that's where we're going to wrap up this video. So, we have this reaction here, where x plus 2y equals z plus 3q. For the reaction represented above, the initial rate of decrease or disappearance in x is 2.8 times 10 to the negative 3 moles, not molarity, moles per liter second. Okay, so first off, reminder, capital M molarity is moles per liter. So we just barely said that the units for rate were molarity per second. And so what if we replace molarity with this? Then that would mean that we have moles per liter per liter second. So same unit. I just don't want you to feel overwhelmed by that. Okay. So we are told that the rate of disappearance of X. So the rate of X is equal to 2.8 times 10 to the negative 3, and we got this like molarity per second. Beautiful. What is the initial rate of disappearance or decrease in Y? Well, look at the equation up here. We have a coefficient of 1, we have a coefficient of 2, of 1, and 3, and we know this one, and we're solving for this one. So let's use those coefficients to look at the comparison between their rates. So we know that the rate of disappearance of X has to equal 1/2, right? Because we have a coefficient of 2, and then we put that in the denominator. 1/2 the rate of disappearance of Y. But to solve for the rate of disappearance of Y, I need to get that by itself. So I'll just divide by 1/2 or multiply by 2. So 2 times the rate of X would equal the rate of Y. All right, easy enough. 2 times by the rate of X. What was it? To the negative third? Yeah. Oops. Okay. Now, I'm noticing my answers are in scientific notation, so let's change that to scientific notation. So that would be 5.6 times by 10 to the negative 3. Right there. All right, everyone. That's where we're going to end the notes for today. Please, please do not forget that on Friday, I'm going to be checking on your digital lab notebooks, that I'm going to be grading the titration lab and the food dye lab. So in Power School on Friday, you're going to get scores for both of those. So make sure this week you go into your digital lab notebook, you add the pictures that are needed, and that you have those ready for me to grade on Friday. If you have any questions, please do not hesitate to reach out, and then I will see you all tomorrow.